business.
Welcome to the Deep Dive, where we transform complex research into actionable knowledge, giving you a comprehensive shortcut to being brilliantly informed. Today we're plunging into one of the most fundamental concepts in, well, all of life sciences, and maybe surprisingly, even engineering and sociology. We're talking about homeostasis. We've got your curated sources here, textbooks, articles, notes, all defining and detailing this powerful biological imperative. So our mission today is to get past that textbook definition, to really understand how living systems maintain this incredibly steady internal environment even when the outside world is just complete chaos. Okay, let's unpack this.
And internal balance is absolutely the key phrase there. I think to really appreciate it, we have to go back a bit, historically.
Okay.
The whole idea that the body keeps its internal fluids constant, he called it the milieu intérieur, the internal environment, that was first described by the French physiologist Claude Bernard.
Right, back in the 1800s.
1849, yeah. And he saw that this constancy was the essential condition for a free and independent life.
So Bernard saw the result, the stability, but he didn't give it the name we all know today.
No, that counts later. The actual word homeostasis was coined by an American physiologist, Walter Bradford Cannon, in 1926.
Mm-hmm.
And he combined the Greek homoios for similar and stasis for standing still, but he was really clear that it wasn't static. It's about stability through change.
That's a huge distinction. It's not a locked-in value. It's a constantly defended average.
Precisely. And if we connect this to the bigger picture, well, think about Joseph Barcroft, who said in 1932 that this stable internal environment is the absolute prerequisite for higher brain function.
For our brains to even work properly.
Exactly. The brain is so sensitive to changes in oxygen, pH, temperature, glucose, you name it. Without homeostasis keeping everything just right, complex thought it breaks down. So it all ultimately serves the brain.
That really raises the stakes.
So how does this whole machine actually work? Your sources all point to three sort of core components. Yeah, you can break down the fundamental control system into a loop that's always running. First, you have the receptor.
The sensor. The
sensor, the monitor, yeah. It detects the change. It could be a shift in temperature, CO2, whatever. Think of thermoreceptors in your skin.
And it's sensing an error, right? Mm-hmm. A deviation from the ideal state.
Mm-hmm. Which brings us to the second part. The control center. This is usually in the brain or a specific gland, like the hypothalamus or the pancreas. Mm-hmm. It gets the signal from the receptor, processes it, and this is the important part. It sets the maintenance range, the acceptable upper and lower limits.
So if the measurement from the sensor is outside that range...
And the control center signals the third component, the effector.
Right.
And that's the target. It can be a muscle, a gland, an organ, and its job is to act to reverse that initial change.
And the whole genius of this is that it's a self-correcting loop. It relies on negative feedback.
Absolutely. The goal is always to reduce the error. So once the effector does its job and brings things back into range, that success is signaled back to the control center.
And it tells it to stop.
It tells it to stop. The negative feedback shuts the system off. If it were positive feedback, it would just keep escalating, which is, a disaster in this context.
Okay, so with that loop, established receptor, control center, effector, and feedback. Let's get into the classic examples. Temperature and energy. We can start with thermoregulation.
Thermoregulation is the one everyone knows, but it immediately shows you that the body isn't aiming for one single fixed number.
That's a great point. We all hear 37 degrees Celsius or 98.6 Fahrenheit, and it sounds like this absolute target.
But it's not. First, the set point itself has a natural circadian rhythm. It's lowest when you're deeply asleep, say between 2 and 6 a.m., and then it peaks in the late afternoon. That daily swing is totally normal.
And the control center, the hypothalamus, can actually override this set point on purpose.
Exactly. Like during an infection, your immune cells release these things called pyrogens, which basically tell the hypothalamus to crank up the thermostat. That's a fever.
So your body then thinks its normal temperature is too cold.
Precisely. It thinks 37 is too cold compared to the new set point of, say, 39. So it triggers all the cold response mechanisms, like shivering, to get you up to that new higher temperature to fight the infection.
So let's talk about those mechanisms. When you're genuinely too cold, what's happening under the skin?
The first and fastest response is intense vasoconstriction. The blood vessels near your skin and in your limbs get much narrower.
To keep the warm blood away from the surface.
Right. It minimizes heat loss to the environment. It's why your fingers and toes get cold first. But then there's this other brilliant system in the limbs.
The countercurrent exchange.
The countercurrent exchange. It's a marvel. The cold blood returning to your core travels in deep veins that are wrapped right around the warm arteries going out.
So the heat just transfers over.
It passively transfers. The outgoing arterial heat gets short-circuited straight into the returning venous blood. It warms it up before it ever gets back to the core, saving a massive amount of energy.
And if that's not enough,
then the hypothalamus calls for more heat production. First, through non-shivering thermogenesis, basically revving up your metabolism. And if that still doesn't work, you get the last resort, shivering, those involuntary muscle contractions.
Okay, let's flip it. What about overheating?
The effectors engage immediately. First, vasodilation, the opposite of constriction. Blood vessels widen to flush heat to the skin. Then, the sweat glands get stimulated by what are called cholinergic sympathetic nerves.
And that detail is important. Why?
Well, sympathetic nerves usually use norepinephrine, but for sweat glands, they use acetylcholine. It's a little quirk. The sweat evaporates, and that is an incredibly effective way to cool down.
But not all animals sweat like we do.
No. Many other vertebrates, like dogs, use panting. That rapid, shallow breathing increases evaporation from the mucous membranes in the mouth and throat. It pulls a lot of heat away.
Now, before we move on, we have to touch on the allostasis. We've been talking about these automatic internal responses.
Right, but allostasis brings behavior into it. It's about achieving stability through change, and a huge part of that is just changing your behavior.
Like seeking shade or putting on a jacket.
Exactly. In extreme situations, that behavioral response is way more important than the physiological one because it's faster and it's energetically cheaper. There's a real cost to constantly running those internal stress responses.
That's called allostatic load, right?
Allostatic load. If you stay in a bad environment, your body pays a price. Allostasis is the idea that the body is smart enough to say, hey, let's change the environment before we break the internal machinery.
That's a profound way to look at it. Okay, let's shift to our second classic case. Blood glucose regulation. This one has to be so precise.
Oh, it's exquisitely balanced. The control center is in the islets of Langerhans and the pancreas. And it's this amazing hormonal duel.
Between insulin and glucagon.
Right. When your blood sugar rises after a meal, the beta cells detect it and secrete insulin. At the same time, they actually inhibit the neighboring alpha cells from releasing glucagon.
So insulin is the signal to store all this new fuel. Where does it go?
Well, insulin is the key that lets glucose into most of your body's cells. In the liver, it slams the brakes on glucose production and tells the liver to start storing it as glycogen.
And if the glycogen stores are full?
Then the liver converts the excess glucose into triglycerides, packages them into something called VLDL, and sends them out into the blood to be stored in fat cells.
What about in muscle and fat cells themselves? How does the glucose get in so fast?
That's the GLUT4 transporter. It's a special protein. Normally, it's just sitting inside the cell. But when insulin binds to its receptor on the cell surface, it signals for all these GLUT4 transporters to move to the cell membrane.
So it basically opens up thousands of little doors for glucose.
Exactly. It creates this massive, rapid influx of glucose out of the blood and into the cells, clearing the sugar very quickly.
And if blood sugar drops too low, that's glucagon's job.
That's the panic signal.
Oh.
Glucagon from the alpha cells targets the liver and tells it to release its stored energy. It does that in two ways. One is glycogenolysis, just breaking down that stored glycogen back into glucose. The other is gluconeogenesis.
Meaning new creation of glucose.
Right. It creates new glucose from other things like lactate from your muscles, or even by breaking down protein, the amino acids, to make sure the brain gets the sugar it needs.
And your sources point out this really interesting detail about muscle glycogen versus liver glycogen.
Yeah, it's all about prioritization. Muscle glycogen is a private fuel tank just for that muscle's use. The muscle actually lacks the enzyme to release that glucose back into the blood.
But the liver is the public utility.
The liver is the public utility. Its job is to maintain blood sugar for everyone else, especially the brain. It just shows you the incredible coordination happening across different organs.
Okay, we've covered temperature and sugar. Now let's get into the really interconnected web fluid, pressure, electrolytes. Here's where it gets really interesting.
They are completely inseparable. I mean, maintaining arterial blood pressure, or ABP, is just central. If it's too low, you don't get perfusion. Too high, and you damage all your blood vessels.
So where are the sensors for this?
The main ones are stretch receptors called baroreceptors. You find them in the wall of the aortic arch and in the carotid sinuses, which are these little bulges in the arteries going to your brain.
And they're just sensing how much the artery is stretching.
Exactly. And the response is almost instantaneous. It's our fastest homeostatic loop. The signal goes straight to the medulla oblongata in the brainstem.
And what does the medulla do?
If pressure is rising, too much stretch, it immediately slows the heart rate, that's bradycardia, and it tells the arterioles to relax and widen. Both things drop the pressure.
And if pressure falls, like when you stand up too fast?
The baroreceptors signal less stretch. The medulla flips to the sympathetic system. You get a faster heart rate, tachycardia, and the arterioles constrict.
And if it's a really severe drop?
Like from an injury, yeah. Then you get a massive sympathetic response that triggers the release of epinephrine adrenaline, which causes severe vasoconstriction everywhere to protect the heart and brain.
And that's the key insight, right? Heart rate itself isn't what's being controlled.
No, it's just an effector. It's a tool the body uses to fix an error in blood pressure. The body isn't aiming for a specific heart rate. It's using heart rate to keep pressure stable.
Which brings us to the kidneys and the famous renin-angiotensin system.
Yeah.
This is where salt and pressure really connect.
They do, and it's a fantastically complex system. The main sensor is in the juxtaglomerular apparatus of the kidney.
Okay, but it's not sensing sodium in the blood directly, is it?
No, and that's the genius of it. It's sensing the sodium concentration in the renal tubular fluid that's about to become urine.
Why there?
Because the amount of sodium that gets to that point is a proxy for your overall blood volume and pressure. If sodium delivery is low, the kidney interprets that as a low volume and triggers the alarm.
And that alarm is the release of an enzyme called renin.
Correct. Renin gets into the blood, and it finds a protein called angiotensinogen, and it cleaves it into angiotensin the versed.
Which is still inactive.
It's just a precursor. The magic happens when angiotensin I flows through the lungs. There's an enzyme there, ACE angiotensin converting enzyme, that converts it into the active hormone angiotensin II.
And ACE is the target for a whole class of blood pressure drugs.
A huge class. ACE inhibitors, they block that conversion, they block the formation of angiotensin II, and that lowers blood pressure by preventing all the downstream effects.
So what are those effects? What does angiotensin II do?
It has two huge jobs. First, it is an incredibly potent vasoconstrictor. It clamps down on arterioles everywhere and jacks up blood pressure immediately.
And the second job?
The second job is to tell the adrenal cortex, the little gland on top of the kidney, to release another hormone, aldosterone.
And aldosterone is all about the electrolytes.
It acts on the kidney tubules, and its job is to reabsorb sodium back into the blood. And where sodium goes, water follows. But it does this in exchange for secreting potassium into the urine.
So it saves salt, but gets rid of potassium.
Exactly. It's vital for preventing sodium loss, but your sources are right to stress that it can't create new salt. You still have to eat salt to fix a deficiency. Aldosterone just stops you from losing more.
Okay, that covers salt and pressure. What about just pure water balance? Osmoregulation.
For that, we look at plasma osmolality, how concentrated your blood is. The sensors, the osmoreceptors, are in the hypothalamus.
And what are they responding to?
They respond to the fact that when you lose water, like through sweat, you usually lose more water than salt. So the fluid left behind gets more concentrated, more hypertonic.
The cells in the osmoreceptor literally shrink a little bit.
They do. And that shrinkage is the trigger. The hypothalamus then releases vasopressin, which you probably know as ADH, antidiuretic hormone.
And ADH tells the kidneys to save water.
It goes to the collecting ducts of the kidney and causes them to insert these little water channels called aquaporins into their membranes. This makes the tubules super permeable to water, so it gets reabsorbed back into the blood instead of being lost as urine.
But again, the kidneys can only conserve water. They can't make it.
Exactly, which is why the second and arguably more important effector is behavioral. The hypothalamus also stimulates the nearby thirst center.
You have to drink.
You have to drink. That's the only way to correct the deficit. And this raises that important question. How do all these systems cooperate? You have aldosterone managing sodium and ADH managing water concentration. They're separate mechanisms with separate sensors, but they have to work together perfectly to keep that internal environment stable. It's just incredible.
So we've seen how elegant these systems are. Let's talk about what happens when they fail.
Yeah.
And also how these ideas have spread way beyond biology. So what does this all mean?
Well, when homeostasis fails, you get disease. It's that simple. And the failure can happen anywhere in the loop.
The classic example being type 1 diabetes.
Right. In type 1, the control center, the beta cells in the pancreas, is destroyed. The sensor works fine, but the effector hormone, insulin, is just gone. So you get chronic high blood sugar, hyperglycemia, and all the damage that comes with it.
What about something less common, like a problem with calcium regulation?
Oh, that's a fascinating one. Calcium is controlled by parathyroid hormone, or PTH. If you get a tumor that overproduces PTH, your plasma calcium goes way up.
And why is that so dangerous?
Because high calcium messes with the electrical properties of every cell. It changes how ion channels and receptors work, making nerves and muscles less excitable.
So it's not just about bones.
No, you get bone loss and fractures, sure, but you also get severe lethargy, muscle weakness, and these classic psychological symptoms, depression, and what they call labile emotions. Your whole system is destabilized.
And then there's the idea of decompensation in chronic disease.
Right. This is when the body's compensatory mechanisms just give out. For years, your body might compensate for something like heart failure. The heart muscle gets thicker, the kidneys adjust fluid, but that compensation puts a strain on everything.
And eventually it breaks.
Eventually it breaks. The heart wears out, the kidneys fail, and you get this rapid worsening of symptoms. The body has run out of tricks to maintain balance.
Which is really, I guess, a microcosm of aging.
It is. Aging is fundamentally a loss of homeostatic capacity. The control systems get slower, less precise. That leads to an unstable internal environment and makes you much more vulnerable to any kind of stress.
Okay, so let's flip from failure to foresight. The sources talk about predictive homeostasis. This is anticipation, not just reaction.
This is where biology gets really clever. It's about responding to an expected challenge. The best example is back with blood sugar.
Okay.
When you eat a meal, even before the sugar is absorbed, your gut releases hormones called incretins.
And these go to the pancreas.
They go to the pancreas and stimulate insulin secretion in anticipation of the glucose that's coming. So by the time the sugar hits your blood, insulin is already there waiting for it, which dampens the spike.
But that's a guess, right? It's an open loop system.
That is the critical distinction. It's an open loop system. It's based on guesswork. And that's why you still absolutely need the classic reactive closed loop negative feedback system to stand by and correct any errors. The anticipatory system makes a guess, but the actual blood sugar level provides the final, precise correction.
And this whole idea of a self-correcting loop, it's obviously not just in biology.
Oh, it's everywhere in engineering. It's the basis of control theory. A thermostat in your house is a perfect homeostatic system.
Sensor, control center, effector.
Yep. The sensor detects the temperature, the control center has the set range, and the effector is the heater or the air conditioner. It runs until negative feedback reaching the right temperature shuts it off.
Cruise control in a car.
Same thing. The speed is the regulated variable. The sensor detects you're slowing down on a hill. The control system tells the effector the throttle to give it more gas.
But the most surprising application for me was risk homeostasis. This is about human psychology.
It's a powerful concept. It says that when you make an environment objectively safer, people often compensate by behaving more riskily to keep their own personal feeling of risk at a constant, comfortable level.
Like with anti-lock brakes on cars.
That's the famous example. The car is safer, but early studies showed drivers with ABS didn't necessarily have better safety records. Why? Because the ABS system removed the negative feedback of a terrifying skid.
So they felt safer and drove a little faster or followed a little closer.
Exactly. They unconsciously traded that extra margin of safety for better performance, keeping their perceived risk level the same. They just moved the boundary of where the negative feedback kicks in.
Which leads to the really big picture idea of societal homeostasis.
Applying this to whole cultures or even systems of knowledge. Think about the constant tension between individual rights and public good. Society is always adjusting laws and norms to try and maintain some kind of equilibrium there.
And Jean-Francois Lyotard talked about this in Science Itself, the idea of stress homeostasis.
Yeah, he argued that established scientific fields are governed by this principle. They resist stress. When a truly radical new idea comes along, it creates intellectual stress because it destabilizes the accepted norms, the set point.
So resisting a new discovery isn't always about being malicious. It's just the system trying to maintain its own stability.
It's the system's drive to maintain its comfortable state of knowledge. It will try to ignore or marginalize the new idea until the evidence is so overwhelming that the set point has to be reset.
Wow. So we've gone from molecules all the way to sociology. It's the same fundamental principle of self-correction.
It is. From gene regulation at the micro level all the way up to these huge complex systems, it's all about that drive towards dynamic equilibrium.
This deep dive has really shown that the body isn't just a machine, it's this incredible self-correcting republic of systems all working together. And as we wrap up, I want to leave you with a final provocative thought from the research. We've just marveled at the body's precise control systems. Instant blood pressure correction, minute-by-minute calcium changes, razor-sharp temperature control. And yet, the sources specifically say that the body's mechanisms for regulating weight homeostasis seem to struggle. They struggle to correct for energetic errors, for short-term calorie surpluses or deficits. So given all these other finely tuned controls we've discussed, why is energy balance the one system where our ancient biology seems to struggle so much to adapt to our modern world? Is it a flaw in a system that was built for an environment of scarcity? Or maybe the system is just designed to average things out over years, not the short term we focus on for our health goals. Something for you to consider the next time you try to adjust your own internal set point. Thank you for joining us on this deep dive into the interconnected systems that keep you alive, alert, and functional. Keep exploring the science,